triangles, as well as proportional lengths that can happen either in triangles or when we have situations with different parallel lines. So yesterday's lesson for the 8-block day, you learned about the angle-angle postulate. So the angle-angle postulate is basically a shortcut that helps us say two triangles are similar without having to sit there and show that all the corresponding angles are congruent, as well as all the corresponding sides being proportional. So it's very similar to our like side angle side congruent shortcut or angle side angle congruent shortcut. So today we're going to learn two more theorems that can help us out with similarity, or two theorems, because yesterday was a postulate. So if you wanted to follow along in your textbook, this starts on page 263. And this is 7.5. So the first theorem we're going to talk about is side angle side similarity. And that says if an angle of one triangle is congruent to an angle of another triangle, and the sides including those angles are in proportion, then the triangles are similar. So when it says the sides including those angles, do you remember when we talked about an included angle was the angle that's formed where those sides meet? That's what that's referring to. So if I just gave you guys two kind of generic triangles so we can talk about what you'd need to look for. First of all, we have to have at least one set of congruent corresponding angles. So let's say maybe angle B was congruent to E, right? Then we also need two sets of proportional sides. So sides that are in proportion, and they need to be the ones that would make angles B and E the included angles. So maybe, for example, the measure of AB, like the ratio of AB to DE, would be in proportion with the ratio of BC to EF. That would make that the included angle, and that could work. So how that would look actually all written out would be something along the lines of if angle B is congruent to angle E, and the ratio of AB to DE is equivalent to the ratio of BC to EF, then we would be able to say that triangle ABC is similar to triangle DEF. So very similar to our side angle side congruence, except instead of the sides being congruent, the sides need to be proportional. Now, in order to check and make sure your sides are proportional, we would just apply our means extremes theorem. So our means extremes property, I'm sorry. So whatever measurements it gave you, you would just want to make sure that if you applied your means extremes property that it would be equivalent. Basically cross multiply, make sure you have equivalent numbers. Side similarity theorem, same idea, except all your corresponding sides are going to have to be in proportion. So if the sides of two triangles are in proportion, then the triangles are similar. So with something like this, there's a few different ways to illustrate it. A lot of the times you'll see an extended proportion. So remember that you have to pick your corresponding measurements. So like AB corresponds with DE, BC corresponds with EF, and I'll pick a different color since I picked a different color before. And then like the measure of AC corresponds with the measure of DF. So now with these, it's very straightforward because your pictures are very neat and oriented in the same way, but sometimes maybe they'll be connected in a bow tie shape, right, with vertical angles. Sometimes you'll have one triangle laying inside of another triangle. Maybe one's flipped around and rotated. So you'll just want to make sure that you know which parts are corresponding before you go and start writing your proportions. It's easy to like just put the wrong number into the wrong place. So what this would look like is if the measure of AB to the measure of DE equals the measure of BC to the measure of EF equals the measure of AC to the measure of DF, then we would know triangle ABC is similar to triangle DEF. So we would need to know that that extended proportion worked, basically. You can apply your means extremes theorem. If you're given values, you could reduce the values, make sure they're equivalent fractions. Lots of ways to check. So that's actually what we're going to do now. We're going to make sure we know how to verify it. Can't do the easy ones, definitely can't do the hard ones. So I just want to make sure we know how to tell if they're similar or not, which similarity theorem you would use, and then make sure we can write our similarity statements properly. And this does show up on your homework. Sure, something like this will show up on your test. So if you take a look, so it says, can the two triangles shown be proved similar? If so, state the similarity. So when it says state the similarity, say triangle, whatever, similar to triangle, whatever. And tell which postulate or theorem you would use. So if you take a look at part A, we have a situation where we have one triangle laying inside of the other triangle. We want to make sure we pick out our corresponding parts. If you're into color coding, this is a great thing to color code on. If not, that's okay too. You just want to make sure you're picking out your proper measurements. Also, very easy little mistake to make here. Is 39 the side of a triangle? No. So should we use the number 39 in any of our proportions? No. Is 27 the side of a triangle? No. So don't use 27 on any of your proportions either. It's easy to be like, to grab those numbers because those are the ones you see. Make sure you're using the entire side measure of the triangle. So first of all, what's something somebody notices here or something you think that we need to verify to make sure that these are similar? Any ideas? Okay, what do you think? Okay, good. Yeah, we definitely have a set of congruent angles here because they overlap at J. Good. So we will be able to say J is congruent to J, and you can write it down if you want, mark it in your picture if you want, or just observe it, either way. Were you going to add something to that, Braden? Mm-hmm. Yeah, that would totally work. So what we're going to do is we want to show that our ratios are proportional, basically, right? So one of your triangles is triangle JFG. So what you're going to do is take one of your sides of triangle JFG, which in this case would be 52, and we're going to write a proportion. Now, when you write your proportion, something to be careful of is you're comparing one triangle to the other triangle. So you want to take 52 and put it in a ratio with the corresponding side of the other triangle, which in this case would be 91, because you would need to add these measurements together. So you could take 52 to 91 and make sure that's equivalent to the other side, which this means you're going to have to subtract 63 minus 27. So then take 36 to your other full side length, 63. So, and you just want to verify that that ratio works. So you would take 52 to 91 equals 36 to 63. Now, there's more than one good way to verify this. First of all, you could just reduce your fractions if you want and see if you could get them to reduce equivalently. I personally think that it's easier to apply your means extremes theorem and cross multiply to check in this one, just because maybe what goes into 52 and 91 doesn't pop into your head necessarily. It's kind of weird numbers. So I would just apply your means extremes theorem to verify cross multiply. 52 times 63 is going to give you 3,276. Right. And then if you also then apply your means extremes theorem or property this way, 91 times 36, you're again going to get 3,276. That shows that our ratios are equivalent. So we have our proportional sides, and we can say that J is congruent to itself. So will we be able to say that these two triangles are similar? Definitely, by side angle side. So we would say yes, by side angle side similarity. Remember, that's squiggle, not an N. My squiggles look like N's. And then we want to also state our similarity, which means like write our similarity statement. For that, again, make sure you pick your corresponding parts. So if I said triangle JFG is similar to, how would I need to name my other triangle? Any ideas? Yeah. Yep, exactly. Triangle JKL. Good. We good with that? Okay. Then for part B, this one, your two triangles are completely separate. There's no overlap. There's no bow tie shape, so there's no vertical angles. So this situation, we don't have any congruent angles, but maybe all of our sides are proportional. Now with something like this, this is one that I personally like to go through in color code so I don't make a silly mistake. Because we don't have our similarity statement, so we're going to need to use our measurements to decide which sides correspond with others. The smallest side in one triangle is naturally going to go with the smallest side in the other triangle. Medium with medium, largest one with the largest one. It's just easy to accidentally grab the wrong number. So here, 10 is the smallest. That would have to go with 25, which is the smallest. And then 20 with 55. And 22 with 55. Or I'm sorry, 10 with 25, 20 with 50, 22 with 55. Okay. It's just nice to kind of do in case your shapes are oriented in a strange way. Especially sometimes when they're done in a bow tie shape, you really got to look, because I've just seen people make silly mistakes with which ones they grab, because they want to almost grab the ones that are always closest to each other. But make sure you verify with their actual measurements. So with this one, we have a few different ways we could verify it. Number one, we could set up several different proportions, right, and apply our means extremes theorem and make sure they're equivalent. Or you could set up an extended proportion and reduce and make sure the ratios are equivalent. It's kind of up to you and what you like best, and also maybe what the numbers are. If you got weird numbers, it might be easier to cross multiply versus reduce. So I'll just kind of show you one way. So we could write our extended proportion, and we have to show that 10 to 25 is equivalent to 20 to 50 is equivalent to 22 to 55. Now these are nice numbers to reduce, right? I can easily reduce each of these fractions. This would be 2/5 equals 2/5 equals 2/5. That's pretty clear to see. And you could, okay, I have equal ratios. This is definitely proportional. But maybe if you had some weird numbers, you weren't sure how they reduced, then you could go through and cross multiply, apply your means extremes property to verify. So now if you do that though, you actually have to do it 3 times because there's technically 3 different proportions here. You would have to apply your means extremes theorem to the first two. Then you'd have to apply it to the second two, as well as the first and last. Okay, so you have to make sure that you verify all 3 and not just like be like, oh, this one works, so it's good. Does that make sense, everybody? Okay. So we can say yes by the side similarity theorem, and I'm going to say that triangle RSQ is similar to, and can someone help me? How would I name the other one if I did RSQ? Any ideas? What was that, Peyton? I'm sorry. CDB. I think so, yeah. RSQ, yeah, CDB, exactly. Good. Why do you say their angles are different? No, not necessarily, because wouldn't angle D correspond with angle S? Yeah. Yeah, that, well, which is, and again, depending on how they're flipped around, reflected, rotated, right? That, hence why I really recommend the color coding for some of them, especially if they're, because it can be a little misleading with, what corresponds with what. So make sure you look at the numbers. But yeah, this one, they would have congruent angles. They're just not provided to you. Does that make sense, David? Yeah. Yeah. So you got to it's kind of like at an angle and reflected. All right, let's look. Any other questions about A or B here? Okay, let's take a look at a little proof. You just have I think like maybe 3 proofs in your homework. They're all pretty short. So this one we are, let me see if I can move this picture down. I don't know why that's hard to read. That's okay. This says, I just don't want you guys to not be able to tell the difference between the R's and the A's. So this says AB to SR equals BC to RA equals CA to AS. I'm not sure why the bottom there got cut off. We're going to prove that BC is parallel to AR. So with something like this, and I think in your homework, you're given a variety of different things to prove. There's one where you want to prove a pair of angles is congruent. There's one where, so I think there's 2 where you want to prove angles are congruent. One again where you want to prove things are parallel. So you want to think about what you need to have parallel lines. Any ideas? What's something we've learned that we can show to prove that 2 lines are parallel? Any ideas? Exactly. We can prove that we have a congruent or supplementary in some cases, right, angle relationship. In this case, Logan's right, it's going to be alternate interior angles. But maybe you need to prove that corresponding angles are congruent. I think that might happen in your homework. Maybe you need to, at some point, show that same side interior angles are supplementary, things like that. But yeah, we're going to prove we have a congruent angle relationship. We can then use our converse theorem, show that our lines are parallel. So good. Now, we're going to need congruent angles, right? Well, don't similar triangles have congruent corresponding angles? So if I can show, or if we can show, that these two triangles are similar, their corresponding angles will be congruent, therefore our lines can be parallel. So let's put our given in here. AB to SR equals BC to RA equals CA to AS. Now, if I tell you this, if I tell you that the measure of BR to RS is equivalent to the measure of BC to RA is equivalent to the measure of CA to AS, what am I telling you? Why is that helpful? The triangles are similar, exactly. They are similar by side, side, side similarity, right? So good. So I know this, so I can then say that triangle ABC is similar to triangle, how would I need to name this? SRA by the side, side, side similarity theorem. Good. And now that I know my triangles are similar, I'm going to have both proportional sides, which I know, great, but I'm also going to have congruent corresponding angles. Which angles would be helpful to say are congruent if I want to show that line BC or segment BC is parallel to AR? Which two should I show are congruent? ASR. So ASR would be this one. And what one was the other one you said? No, I think we could maybe do that one. Because yeah, you'd have, I mean, oh no, that would show that AB was parallel to RS. Because your Z shape would end up here. So take that again, kind of like flip it around. Anybody? Julia? Yeah, BCA and RAS would work. So BCA, right, is here. So you'd have your Z shape here. Cool. You just were looking at the two wrong sides, Logan. You're good. Good. So we are going to say that, erase all these squiggles here, that angle BCA is congruent to angle, if I say BCA, I should say RAS. Good. So angle BCA is congruent to, not triangle, angle RAS. And how you write, this is up to you. You can, again, you can always write an explanation. So you can say corresponding angles of similar triangles are congruent. This is though also part of the definition of similar polygons. So you can also just cite definition of similar polygons. Up to you what you say there. Then if I know my angles are congruent, I can say my sides are parallel. And who remembers what an appropriate reason for that would be? Julia, what do you think? Yep, you can either say converse of the alternate interior angle theorem, or I would also accept alternate interior angle theorem converse, however you prefer to say it. And again, an explanation is always appropriate as well. You can say, if alternate interior angles are congruent, then the lines are parallel. And that's pretty much how those proofs will go. Sure. Okay. I mean, you can call them alternate interior angles if they're alternate interior angles. I guess I'd have to see the diagram, Braden, but you can't automatically say they're congruent unless you have other information. Like if you know the lines are parallel, then yes, you can definitely say they're congruent. Or if you know the triangles are similar, then yeah, you can definitely say they're congruent. If you tell me which one later, I can always look at it too. All right, so on to 7.6. This starts on page 269. We are going to now look at proportional lengths. So some of these lengths will happen in triangles, some of them are formed by parallel lines. We got two theorems. So we have the triangle proportionality theorem to start. This is, if you're looking at the textbook, there's this little part that like defines divided proportionally. I didn't think we needed to define that. I think that if things are divided proportionally, guess what? They are split up proportionally. That's what that means. So I didn't think that that was something we needed to formally define. So first we have the triangle proportionality theorem. That says if a line parallel to one side of a triangle intersects the other two sides, then it divides those sides proportionally. So this is basically saying that if segment PQ is parallel to segment RS, then either side of your triangle is being split into proportional parts. So how this would look formally is we could say if segment PQ is parallel to segment RS, then the measure of RP to, that got cut off on mine. That should be a T. You guys can see it on the copy I posted, right? I don't know if you downloaded it. If you didn't, that should be a T. My Microsoft Word on my HP Pro book is, I don't know, there's something going on with the margins that I need to figure out how to fix. So the measure of RP to PT equals the measure of SQ to QT. So basically your sides get split up proportionally. The ratio of RP to PT is going to be equivalent to the ratio of SQ to QT. Now something else that happens, that's not the only proportion you could write here. These smaller parts are also going to be proportional to the entire side of your triangle. So there's a few different proportions you could write. Another example is we could say that the ratio of PT to RT equals the ratio of QT to ST. That would be another example. So the smaller parts get split up proportionally, but they're also proportional to the entire measurement. So RP is proportional to both PT, or I'm sorry, the ratio of RP to PT works, but the ratio of RP to RT also works, right? So sometimes you'll hear me refer to it as like the small part to the medium part to the whole thing, or small to large to whole. So it's also proportional to the entire length. Okay, so you'll see a few different ratios written there. Triangle angle bisector theorem is the next one. And that says if a ray bisects an angle of a triangle, then it divides the opposite side into segments proportional to the other two sides. So here we have this case, it's a segment, but we'll pretend it's a ray. So we have a segment that is bisecting our angle here. We can see we have our congruent angles. And what happens is it divides the side that it intersects proportionally to the other two sides of your triangle. So your ratio of C to D is going to be equivalent to your ratio of A to B. And because of how our proportions work, this is again not the only way you could set this up. We could just as easily say A to C is equivalent to B to C, if you want, or B to D, I'm sorry, B to D. Okay, or flip that around in a variety of different ways. So this could be done really in any of those ways. Okay, so, but traditionally, this is the main way you will see this set up. So this side is split proportionally to the other. Okay. All right. Questions about either of those theorems? No. All right. Last thing is a corollary. It's actually it's derived from our original theorem. And also too, this picture and like this picture, they might look familiar to you because their properties are kind of similar to when we talked about mid segments, but instead of they're going through the middle, instead of things being broken up congruently, things are broken up proportionally. So here, our last thing, our corollary, is if three parallel lines intersect two transversals, then they divide the transversals proportionally. So very similar to our first theorem, except this time we have three parallel lines instead of just the two. And basically, again, everything's going to just get split up into proportional parts. So what we would say on something like this is if line T is parallel to line U, that doesn't really look like U. It's parallel to line U is parallel to line V, then the ratio of AB to BC would equal the ratio of DE to EF. So your parts get split up proportionally. However, the same thing is going to happen where these small parts are also proportional to the whole measurement. So you could also write this proportion in other ways, like for example, AB to AC equals DE to DF. So it's also proportional to your entire measurement. And really, which ratio you use, or I'm sorry, which proportion you apply, is going to depend on what information you're given. Right? Are you given the smaller parts? Are you given the entire measurement? Some combination of all of it. So it's just going to depend on what you're trying to find. Okay. Any questions about how that works? We're good. We just have 3 examples and then we're done. Ready? Okay. All right. So number 1, solve for the variables. Here, this one, you can see we have our congruent angles here. So this says apply the angle bisector theorem. This segment's going to be your angle bisector. So we have our proportional parts along the side that's being split up to the other 2 sides. Now, first thing, and the reason I gave you this one is because do we really want to use 3x plus 15 in our proportion? No, we're going to need to use this as well as the 21 to find a value for this missing piece. So how could I basically provide a label for this little missing section that we need? Any ideas? Yeah, precisely. Just take the whole thing minus the part. Don't overthink it, right? 3x plus 15 minus 21. So we can go ahead and simplify that to 3x minus 6, right? And now we can just easily set up our proportion. apply your theorem. Remember, this side gets split up proportionally to the other two sides. So, and more than one good order to do this in, but I'm going to do 3x minus 6 to 21 equals 48 to 28. Now, I have complete faith that you guys can apply your means extremes theorem and multiply this. Really, the reason we're looking at it is number one, I want to make sure you have your setup right. Number two, if you want to reduce these fractions before, could you? Yeah, and I just want to show you guys that that's an option. You could reduce both sides of this if you want. You could reduce just the 48 over 28 if you want. Really doesn't matter. But personal opinion, smaller numbers are better. So you could reduce maybe this entire left-hand side by 3 if you wanted to. So why not, right? Maybe change this into x minus 2 over 7 equals, and then we could reduce this proportion as well. What would go into both of those? 8? Does 8 go into? What are you going to make it? Sorry. 12 over 7? Yeah, oh yeah, 4, just 4 goes into both of them, 8 doesn't go into it. Yeah, 12 over 7. And then actually, you could just see that x would be 14. Or keep cross multiplying. It doesn't matter. Okay, so I just want to show you there's a lot of different good ways to solve this. Are we okay with the solving part of this, or do you want me to like walk through each of the steps? Technically, sorry, I cut you off. What were you going to say, Hillary? Oh, okay. Well, technically, you're just going to apply. Well, so do you understand how we reduce them? Okay. And this part's completely optional. If you don't want to do it, you don't have to. We're basically going to apply our means extremes property and cross multiply is what we're going to do to find x. So if you apply your means extremes property here, we would have 7x minus 14, and then apply your means extremes property here to get 84. And then we're just going through and we're solving. So that's 98, and then that would be 14. So pretty much just applying that means extremes property to cross multiply. Does that make sense now? Oh, okay. No, that's okay. And there's more than one good way to set these up. And also too, there's some of them that if the numbers are simple enough, you could probably even just look at the ratio and be like, oh, these sides have a, not in this case, but just in general, these sides have a 1-to-2 ratio. So this will have to have a 1-to-2 ratio, and use some number sense. So it's kind of up to you. I'm not gonna force you to write a certain kind of proportion because there's so many different things that could work. All right, so if you take a look at B now, this is our triangle proportionality theorem. We have our parallel lines, which means our sides get split up proportionally. So again, several different good ways to set this up. For example, I have a tendency to start with the part I don't know. So that would be this little part here. So 3x minus 12 to 35 equals 9 to 15. And again, you could reduce your fraction if you wanted to. We cannot reduce the left-hand side, but you could reduce the 9 over 15 if you wanted to, if you don't want to have to distribute a 15. Why would you want to distribute a 15 if you didn't have to? So we could easily reduce this down to 3 over 5 if you wanted to. But again, completely optional. Are we okay with what I just did there? No one just like looked away, looked back, and went, whoa, she has different numbers now? Okay. Okay, so then I'm just going to apply our means extremes property and get 15x minus 60 equals 105. So 15x equals 165. And we're going to say that x equals 11. How do we feel about that one? Yep. Ashley, you just look so excited. All right, and then last one. Again, this exact same idea, slightly different diagram. This one, this is our corollary. So you literally do the exact same thing. And again, base how you write your proportion off of the information you're given. You know, if I'm trying to think of something you might see occasionally. Maybe if the entire side is labeled, right, you might need to see, okay, can I figure out what my entire measurement is on the other side? And vice versa. What's just really important with these is make sure you have matching information, right? If I have my little part over here, I need my little part over here. If I have my little part down here, I need my little part down here. If I know what, if I'm trying to find X and X is the entire measurement, then I'm going to need to know what my entire measurement is on the other side. So just make sure your information matches. So here I'm going to do 3x plus 8 to 20 equals 21 to 12. Again, we can reduce our numbers if we want. Again, I don't want to multiply by 12 if I don't have to. So I'm going to reduce this side down. What 3 goes into both of them? So it'd be 7 to 4. Completely optional. But why work with big numbers if you don't have to? And now it's so much easier to cross multiply. So that would be, you can almost think of this as like a scale factor. It's not really your scale factor because we're not looking at similar shapes, but it's a very close idea to that. So that would give you 12x plus 32 equals 140. 12x equals 108. And divide that to get 9, I believe. 108 divided by 12, yes, 9. Okay. And yeah, there's a chunk of those. There's a chunk of deciding whether a proportion is correct or not. They're going to give you just some different like generic measurements like in forms of letters, and you have to decide, did they pick the parts that correspond properly? There might be one factoring one. If I'm looking at number 23 correctly, this is page 270.